So in the gold foil experiment, in this experiment you've got this chamber set up so it's completely encapsulated except for a small hole. And there's a sample of matter in here, some radioactive material. So the word radioactive just means it's able to emit energy. Usually that means it's emitting energy from the nucleus. So at this time, there's no idea that atoms had a nucleus, which seems really weird to you probably because your entire life and in any science class you've had, talk about the nucleus, right? The protons and neutrons are in the nucleus, the electrons are on the outside. So how did they discover the nucleus? How did they get evidence for the existence of the nucleus? You can't see an atom, you can't see a nucleus. There's got to be some experiment that shows the nucleus is real and it exists, and that's what the Rutherford Gold experiment was all about. So this experiment was set up to kind of test a hypothesis. So good science is based on having a model or a hypothesis or an idea about how things work or an explanation for why things work the way they do, and then trying to come up with an experiment that can test that out. So the original idea at the time was the so-called plum pudding model. The plum pudding model, the idea was in an atom, which is like the smallest particle of matter, these protons and neutrons and electrons are all just kind of spread out. So originally there was no idea of a nucleus. Just take the particles that we know are an atom based on how heavy it is and what its charges are, and imagine them just being spread out around the atom. If that model or hypothesis were correct, if everything is spread out throughout the atom, there shouldn't be much to block a particle that might be passing through that sample. Right, so the hypothesis was, if I shot tiny particles at this very thin piece of gold, if all the particles of the gold are spread out, then the tiny particles should pass right through the gold, and they shouldn't be deflected. So if I have a very thick piece of gold, then it might cause some deflection. But the idea was to create a very thin piece of gold, only a few atoms thick, so if we have these tiny particles passing toward it, they would maybe go through the gold. Well, what was found instead was as the particles that come out of this box, the radiation particles, fly toward the gold, a lot of them did make it through, but many of them were reflected back at a variety of angles. So that suggested that there are areas in an atom that are deflecting or repelling the approaching particles. Okay, so it was known that the particles coming out of this box that they're firing at the gold had a positive charge. And if we see these positively charged particles deflected back somewhat, that suggests that there are areas in the atom of concentrated positive charge. So when these positively charged alpha particles fly in toward this gold foil, if they get close to another positive charge, the repulsion causes them to turn away. And so here's the simulation that kind of shows that visually. So if I turn this gun on, so basically what's happening here on the left-hand side is this gun is shooting the alpha particles, and I've got my gold foil here, so this is just like showing it from a macroscopic scale. And then they're zooming in on one of the gold atoms to show what happens when the alpha particles approach it. So we've got this wide spray of alpha particles. The ones on the side pretty much going straight through. The ones that approach the nucleus, though, they kind of get deflected back. They might get deflected out at an angle. They might get more deflected straight back. It depends on the angle of approach. So if an atom has these nuclei in it, where all the mass of the atom is concentrated and all the positive charge of the atom is concentrated, that blocks out some of the alpha particles. Why doesn't it block out all of the alpha particles? Why is it that some of these alpha particles are making it through? Yeah, relative to the size of the nucleus, there's a huge amount of empty space around it, right? So this is just one nucleus in the gold foil. So I've got a foil here. I've got a thin piece of gold. It's a solid. In a solid material, we think of the particles being close together because they're attracting, right? So they're attracting, they're close together in a solid particle, but the nucleus is so small and is surrounded by a pretty much mostly empty space, that the distance between this nucleus, if this were the size of it, like if I blew up the nucleus and zoomed in on it and looked at it at this size, the neighboring nucleus in the next atom over in this solid where the atoms are packed close together, the neighboring nucleus might be or in the next room or something. So there's a ton of empty space between these nuclei, and the alpha particles, if they go between the nuclei, they don't feel any repulsion because they're not close to that positive charge, they just fly right through. So a lot of the alpha particles just flew right through the foil because there's nothing there. But the few that were flying at an approach that was taking them toward the nucleus got either deflected back or deflected out at an angle. And Rutherford was able to calculate, based on how many went through versus how many deflected back and all the angles that they deflected back with, using some math, to calculate exactly how big the nucleus was inside of each atom. So that's the Rutherford Gold experiment. The idea here was, and this is an exaggeration. So this is not to scale, right? So this picture here is nice because it shows, it allows you to see that when the alpha particles come in, they're not all just flying through, right? Some of them are approaching the nucleus and getting repelled backwards or to the side. But this is not really to scale for what the nucleus actually looks like. Yeah, 1 second. This is to scale. If you blow up and zoom in on an atom, and this is its nucleus, this is how much empty space is around it. And so if I take this and put it next to another atom, and imagine where its nucleus is, there's a huge amount of empty space between those nuclei. That's to scale. Questions about that? Yes?
Does this experiment take a long time?
It doesn't really take a long time. It really would depend on the radioactive material that you use. There are some radioactive elements that release alpha particles at a pretty fast rate, and some that release alpha particles at a much slower rate. So if you choose the right radioactive material, you could get enough alpha particles to be coming out of there in a relatively short period of time. Here? Yeah, so this is similar to the screen in the cathode ray experiment. So you've got this screen that surrounds here with a fluorescent dye on it. So if an alpha particle comes through here, you can't see it interacting with the gold foil. All you see is where the screen is lighting up due to the energy of the alpha particle hitting the screen and exciting the molecules on the screen and causing a little bit of light. So you have to use some type of device to determine how much light is in these different spots and what the intensity of that light is to determine how many collisions are occurring with the screen and in which area. Yeah. So when we're talking about radioactivity, different elements have the ability to emit different types of particles because of the way their nucleus is constructed. So when you take protons and neutrons and put them in a nucleus, you have to have a number of protons and neutrons that's a stable number. And for each element, that's a different number. So what defines carbon is the fact that it has 6 protons. If you have an atom with 6 protons, that is always carbon. If you have more protons, it's not carbon. If you have less protons, it's not carbon. But with the 6 protons that are in carbon, it could have any number of neutrons with those 6 protons. If you have 6 neutrons with the 6 protons, or 7 neutrons with the 6 protons, those are stable atoms. They're not radioactive. That number of protons and neutrons is a relatively stable number that's not going to release any energy or particles. But if I put 8 neutrons with the 6 protons, now I have an unstable nucleus. For some reason, that number of protons and neutrons together in an atom is not stable. It won't stay that way. And so that nucleus with 8 neutrons and 6 protons will give off beta particles, which are the same as electrons. Those electrons are not emitted from the electron cloud around the atom. those electrons are emitted from the nucleus. There's protons and neutrons in that nucleus, and that number is not stable. So what happens is one of the neutrons, because it's got too many neutrons in its nucleus, one of the neutrons will emit a negatively charged tiny little beta particle, and if it emits a negative charge, a neutral neutron with no charge emitting a negative, losing a negative, now will become positive, and it becomes a proton. So in the carbon-14 nucleus, a neutron becomes a proton as it emits a beta particle. So, not to get into too much detail on that, but all the different elements, if those, you could take any element on the periodic table, if you set it up with a number of neutrons that's not stable for that element, it will be radioactive. So you can have a variety of different radioactive substances. For this particular experiment, the one that emitted alpha, beta, and gamma, they used a radioactive element. I don't know which one, it doesn't really say in the textbook. But they used one of the elements that, when it's radioactive, it has the ability to release more than one type of radiation.
It was beryllium, I believe.
Oh, okay.
Yeah.
So whatever isotope of that element that they use, sometimes the atoms become more stable by emitting alpha particles. Sometimes they become more stable by emitting beta particles. And sometimes in the process they also emit gamma rays, which are just a form of high energy light. So it can give off light energy, it can give off positively charged particles, it can give off negatively charged particles. Whatever it needs to do to adjust the number of protons and neutrons to become a more stable number, to make a more stable nucleus, that's what a nucleus that's radioactive will do. And so in this simple experiment, they just took that element emitting those types of energy, focused its beam into a very narrow beam, and made it pass through a potential where I've got a negatively charged plate and a positively charged plate, to see that some of the particles of radiation coming out got attracted to that negative, and that altered their path toward that negatively charged plate that attracted them. And other particles were altering their path toward the positively charged plate that attracted them. So that just shows that inside an atom, there are some positively charged particles, there are some negatively charged particles, and there are also, if the atom is unstable, the ability to emit just pure energy in the form of light as it becomes more stable.